All right, get ready to dive deep. Today, we're tackling the normal distribution.
Oh, yeah. The bell curve. Classic.
Classic indeed. But I gotta admit, it's always kind of felt like magic to me. Like, how did we even figure this thing out?
Well, you sent in this video by PakapongZa that really breaks it down, goes back to the OG, Carl Friedrich Gauss.
Yes, huh?
Huh?
So this wasn't just some random thing statisticians pulled out of thin air.
Nope, it all started with a real-world problem. Measurement errors.
Errors, like messing up the measurements.
Think like astronomers back in the day trying to pinpoint a star's location. Every measurement's a little off.
Ah, so how do you know which one's the real position?
Exactly. And that's what Gauss was grappling with. How to represent a bunch of measurements, all with their own little errors, with one single value that makes sense.
Sounds like a statistical nightmare.
Well, the video uses this cool analogy, a balance scale. Imagine each measurement's like a weight you put on the scale.
Okay, I'm picturing it.
And the goal is to find that perfect balance point, that central point representing the whole set of measurements.
So is that balance point like the average, the mean?
Boom, you got it. That's the mean. But here's the thing about Gauss. He didn't just stop there. He wasn't content with just the average. He got curious about the errors themselves.
The errors, like what's interesting about being wrong?
Well, he started visualizing them, like plotting them on a graph. And get this, a pattern emerged, what we call an error curve.
Hold up, so randomness itself can be predictable.
It's wild, right?
Right.
And that curve, that's basically the foundation for the normal distribution. To really get how he got there, we got to look at his assumptions about these errors.
Assumptions, huh? Like what was he working with?
So first off, he figured small errors are way more common than big ones, like more likely to be off by a little bit than a whole lot.
Yeah, that makes sense. If you're measuring something, you're not going to be off by like a mile.
Right. Second, he assumed the errors are symmetrical, meaning overshooting the real value is as likely as undershooting it. No bias either way.
So kind of like a coin toss. Heads or tails, 50-50.
Perfect analogy. And lastly, he assumed that if you just keep taking measurements, they'll bunch up closer and closer to the true value.
More measurements, closer to the truth. Makes sense to me.
Right. So we're building this picture of how errors behave. But then the video drops this term, density function. Sounds kind of scary.
Density function.
Yeah.
Yeah, that doesn't exactly roll off the tongue. What's that all about?
It's simpler than it sounds, really. It basically tells us the probability of different outcomes happening. Think of it like flipping that coin again. Heads or tails, each got a 12 probability. The density function would be a way to show that visually.
Okay, starting to click. So with Gauss, he was looking for the density function for those measurement errors, right?
Dringo, he wanted to figure out how likely is it to get an error of a certain size. And to do that, he used this brilliant idea, maximizing probability.
Maximizing probability. Lay that on me.
Basically, he reasoned that the real value, even though we don't know it for sure, should be the one that makes the errors we actually observe the most likely. Does that make sense?
So the true value should be the one that best explains the pattern of errors we see. I think I'm getting it.
You're getting it. And, the math gets a little complicated here, differentiation, all that fun stuff. But the crazy thing is, from this whole maximizing probability thing, the shape of his error curve pops out naturally.
No way. It's like he's conjuring up a fundamental concept out of thin air just by thinking about how we make mistakes.
It really is kind of magical. But there's a twist. The function he got wasn't exactly the normal distribution formula we use nowadays. It's close, though. Real close.
Close, but no cigar, huh? So how do we get from his error curve to the classic bell curve we see everywhere?
Well, that's a story for part 2.
All right, folks, we're just getting warmed up. Hang tight. We'll be back in a flash to keep unraveling this statistical mystery. Okay, so last time, minds were blown. Gauss basically found this hidden pattern in measurement errors.
Yeah, he found the seed of the normal distribution, but like we said, the formula he came up with wasn't exactly the one we use today.
Right, right. So how do we get from his error curve to the, the superstar bell curve we see all over the place?
It's kind of like he discovered this rare flower out in the wild.
Okay, I like where this is going.
And later on, other mathematicians, they kind of cultivated a whole garden from it. Like a whole bunch of similar flowers, but, different varieties, all part of the same family.
So Gauss's error curve is like one specific type of flower, and the modern normal distribution, that's the whole, the genus or something?
You got it. And this genus, it's got a more flexible formula. That's why we can use it for all sorts of data, not just like astronomy stuff. That's what makes the normal distribution so powerful.
Okay, so spill the beans. Where else does this normal distribution thing pop up? Like real world stuff?
Oh man, where do I even begin? It's everywhere. Take human height, for example. You plot the heights of a whole population, you'll see most people cluster around an average height. Fewer people are at the extremes, super tall or super short.
Yeah, yeah, that classic bell curve. We all know folks who are way taller or shorter than average, but most of us are kind of in the middle.
And this pattern, you see it in tons of natural stuff. Blood pressure, IQ scores, even snowflake sizes. They all tend to follow this normal distribution thing.
Wow. So it's not just describing stuff. We can actually use it to, like, analyze and predict things, right?
Exactly. Let's say we know the average height and how spread out the heights are in a population. We can actually estimate how many people fall into a certain height range.
Okay, that's pretty cool. So we can figure out, like, how many people are between, say, 5'5" and 5'10".
Exactly. And it goes way beyond just nature. Think finance, modeling stock prices, assessing risk.
No way. So this normal distribution is like a secret decoder ring for understanding all kinds of stuff.
It kind of is. But, and this is important, it's not a universal law or anything.
Right, right. Not everything fits perfectly into that bell curve.
Like wealth distribution, that's usually skewed. A few people have a lot, most have little. Doesn't fit the normal distribution.
So you got to use the right tool for the job. Or
Always. Knowing what a tool can't do is just as important as knowing what it can do.
I'm telling you, this whole deep dive has given me a whole new respect for the normal distribution. It started with an astronomer trying to figure out where a star really is, and look where we are now.
It is pretty amazing, right?
Yeah.
A simple question leads to this huge concept with applications everywhere. But speaking of simple questions leading to crazy discoveries,
Uh-oh. I sense another twist coming.
get this. The normal distribution pops up in a totally unexpected place. Quantum mechanics,
Hold up. Quantum mechanics, like the world of tiny particles.
the one and only.
Yeah.
And that's where we're headed next.
All right, folks. We're about to go subatomic. Hang tight. We'll be right back for the final part of our deep dive. Okay, deep breath, everyone. We're going quantum. Last time, we kind of blew my mind with this idea that the normal distribution shows up in quantum mechanics. Like the same thing that describes star positions and people's heights is connected to the tiny world of particles.
Yeah, things are going to get a little weird here. We're talking subatomic particles, the quantum world. Things work differently down there. But even in that weirdness, the normal distribution pops up.
But how can a statistical tool, something that describes patterns in big groups, be relevant to individual particles? It's like apples and oranges, right?
It's a wild connection, shows how different areas of science kind of intertwine. See, in quantum mechanics, particles, they can exist in multiple states at once. It's all probabilities, and you can't know everything about them at the same time. Like their exact position and momentum, it's all fuzzy.
My brain's already hurting.
Yeah.
So where does the normal distribution fit into all this quantum fuzziness?
Well, there's this famous principle, the Heisenberg uncertainty principle. It says there's a limit to how precisely we can know both the position and momentum of a particle.
Yeah, I've heard of that, but it's always been super mysterious to me.
It's a mind bender for sure. But here's where the normal distribution comes in. Those uncertainties, they're not just random. They follow a pattern. And guess what describes that pattern?
Don't tell me. The normal distribution.
Ding, ding, ding. It comes right out of the nature of quantum uncertainty. It's like the universe is playing a game with dice down at the subatomic level, and the normal distribution, that's the rule book.
So even in this quantum world, where everything's probabilistic, there's still some underlying order, like a statistical heartbeat.
I love that, a statistical heartbeat. And it goes deeper than just the uncertainty principle. In quantum field theory, the theory that describes forces and particles, the normal distribution pops up there too. It's used to calculate quantum fluctuations.
Quantum fluctuation. Okay, now you're really throwing me for a loop.
Think of it like this. Even in empty space, there are these tiny energy variations, things popping in and out of existence all the time. It's like a constant buzz of activity, but at the quantum level.
So even in the void, there's this dance of particles appearing and disappearing, all based on probabilities.
And what describes those probabilities? The normal distribution. Again, it's like this multi-tool that connects all these different parts of physics and statistics.
I gotta say, we started with an astronomer trying to figure out where a star is, and now we're talking about the very essence of reality. And the normal distribution has been our guide the whole way. It's like a secret code in the universe.
It really shows how powerful math and statistics can be. Who knew that study and errors could lead us to such incredible insights about the universe?
It makes you wonder what other connections are out there, just waiting to be discovered, right? Like, what simple question will lead to the next big breakthrough? That's what's so cool about these deep dives. You never know where they'll take you.
Exactly. The thrill of the unknown. And remember, the search for knowledge never ends.
Couldn't have said it better myself. And a huge thank you to you for walking us through this amazing world of the normal distribution. I'm seeing it everywhere now. And to our listeners, thanks for joining us on this incredible journey. We hope you've gained a new appreciation for this hidden code, this normal distribution that shapes so much of our world, from the tiniest particles to the vast cosmos. Keep exploring, keep questioning, and keep diving deep. Until next time.